What's up, guys? Today we're doing a question currently being asked by Amazon, Microsoft, Google, and a whole bunch of other companies, and the question is called house robber. Let's get to it. What's up, guys? Today we're doing a question currently being asked by Amazon, Microsoft, Google, and a bunch of other companies. I've currently had a friend ask this question in a final round at Amazon, so it's a really important question to understand and know how to do. So just to hop into it, the problem description is: you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given a list of non-negative integers representing the amount of money of each house, determine the maximum amount of money you can rob tonight without alerting the police. So for this example 1, which are the nums 1, 2, 3, and 1, our output would be 4 because we could rob houses at index 0 and 2 without robbing adjacent houses and maximizing the amount of money that we can make robbing houses tonight. So I want to go over more than just the bottom-up solution with DP, dynamic programming, that I was thinking of doing that could honestly be done in 2 minutes, because during these interviews it's not always immediately clear what the bottom-up decisions you want to be making are. So because of that, I wanted to talk about a framework that you could use in order to be able to always just understand the recursive decisions and then take this top-down recursive solution, add memoization, and then change it so it's bottom-up so you can get that best runtime scenario, even if you've never seen the problem before or have no clue what the bottom-up decision would be. So just to start out with our top-down solution, which is pretty simple, we want to think about, and I've talked about this same framework when doing combinatorial problems like combination sum, but this can be used in optimization problems like this as well. So we want to think about the state, our base cases, and our decisions. So in this case, our state is just the nums array and our current location in the nums array, which is just, I could call it I, or I could call it current location. And then we want to think about our base cases, which in this bottom-up case is literally just if we're starting from the end and then moving backwards, if I is less than 0 would be our base case, and we just want to return 0. And then our decisions would just either be that we pick current house, and that would just be picking the house at our current iterator. So it would just be like nums at I plus a recursive call to some helper at nums, could we keep that constant in I minus 2, or just skipping the current house. And that would just be not adding nums plus I, no, nums at I, and just calling our helper at nums I minus 1. So the way we just do this is we want to make some call to our helper. So say return helper at nums, and then if we're starting the end, it would be len nums minus 1. And then just to implement this helper, we'd say def helper nums I. We'd implement our state, or our base case, so if I is less than 0, return 0. And then we'd have our pick house case, which would be nums at I plus helper at nums I minus 2, and skip house decision, which is just our helper at our nums and I minus 1, because we'd go 1 house back. And then in order to maximize the amount of money we'd make, we just pick our max of our pick house and our skip house case. So this should work, but one thing we'll see, and let's see if this works. So yeah, cool, so this works. And one thing we'll see is if we were to run this on everything, we'd actually see this timeout because there's so many recursive calls to the call stack, and we're recomputing subproblems. So if I made a problem tree and I'll put one up here for this problem, we'd actually just time out because we'd be recomputing so many subproblems. And because of that, we'd want to be able to make sure that we wouldn't have to do this. So we'd want to do something like create a memoization array, or a memoized array. So we could say memo equals -1 for I in range len nums, and then the case we would just add is elif I, or elif memo at I is greater than or equal to 0, because we set everything to -1, then we just return memo at I. So now we wouldn't have to recompute the subproblem. And then first here, we'd want to just set our memo at I equal to this max, and then return our memo at I. So this should help change our runtime for our bottom-up case, or our top-down case, which was originally 2 to the n, because we get 2 to the n subproblems, to be just O of n. And then our space would again be O of n for the space in our memo array, but we need an additional n for the n calls to the call stack, which would just be 2n, which is still n in big O analysis. So now if we wanted to take away these n calls to the call stack, we can then use these decisions again. So these are the top-down state base cases and decisions. But if we wanted to change this, so we could do this for top-down with memo, our approach 2, we could just have an added base case, elif memo at I exists, then we can return memo at I. And then we just store this base case at the end of our decisions. But now we'd want to do this for a bottom up. So I'm just going to store this guy top down memo. But let's do this for a bottom up case, because this would improve it wouldn't improve our big O runtime, but it would improve our runtime. So in order to do this, we still want to be keeping track of our state, but we'd want to be doing this without calls to the call stack. So instead, our iterator will be in something like a while loop or a for loop. So we just set up our base cases here. So like if not nums, we just return 0. If len nums is equal to 1, we'd return nums at 1, or nums at 0. And then otherwise, we'd want to create this memo array. So we'd say memo equals -1 for I in range len nums. And I could probably say, I'll just say 0 actually, because if we're not picking a certain index, it's not going to be negative, it's going to be 0. And then we can just say for I in range 2, because we already we can set the value for 0 and 1, because for example, our memo at 0 is going to be equal to nums at 0, and our memo at 1 is going to be equal to the max of nums at 0 and nums at 1. So we can say for I in range 2 to len memo, we can just set our memo at I equal to the maximum of these 2 decisions that we've talked about. So now we're actually going to go back to these decisions, the pick house, the pick current house, and the skip house decision. So the pick house decision would be that we select house at I plus, and then we say plus our memo at I minus 2, and then our skip house decision would be that we pick the house at, or the subproblem at I minus 1. And then at the end of this, we just return memo at -1, and then this should be good. So let's run this, see if it works on the first case. Great, and it does. And let's run this and see if it works on everything. Great, and that works. So I hope that made sense, guys. It's really important to understand how you come up with top-down solutions and how you understand the state base cases and decisions you're making to be able to create bottom-up solutions for any problems that you're trying to do. I hope that made sense. So if you have any questions, just leave those in the comments down below. This is a really important question. So let me know if you have any of those. And if not, I hope you like this. Give this a thumbs up and subscribe if you want to see more. And I'll hopefully see you guys again soon. Have a good one. Peace.